So, welcome to Chapter 5. We're going to pick up where we left off at the end of Chapter 4, continuing to talk about probabilities and probability distributions. So, we know what a random variable is. We've talked about this. This is any variable, and a variable is something that we don't know that we're looking for, that assigns a numerical value to an outcome of an experiment. So, we're going to denote that by an uppercase X or uppercase letter. Usually we use an X. Sometimes we use a Y if we have more than one variable, but X is kind of the norm. So values of a discrete random variable would be the lowercase x. And so if we had three values, then we would have x1, x2, and x3. So we'll look at some examples of this here in a moment. Now, variables may be discrete or what we call continuous. Discrete variables are countable. They have a distinct set of values. So think if I rolled a die and you get a 1, 2, 3, 4, 5, or 6. Those are discrete. Continuous variables, and we talked about these way back in Chapter 1, they are not countable. So there's an infinite number of variables that it could possibly be. So let's look at a couple of experiments. So the first one is we roll a six-sided die, like if you were playing a board game or something. So your sample space here is rolling a 1, a 2, a 3, a 4, or 5, or 6. So these variables are finite. There's a limited number of them, and they are countable. So this is a discrete probability distribution. In experiment 2, we're looking at two shirts on a production line. We're going to identify those as defective with a D or non-defective with an N. So these are the sample space would be you draw two defective ones. You draw one that's defective and one that's non-defective. You draw one that's non-defective and one that's defective. And then we have two that are non-defective. So these are also finite and countable variables. And in experiment 3, we're reviewing mortgages. And so we say that they can be either approved or denied. Now, this is countable, but infinite. We could, in theory, get an infinite number of mortgage applications. So there's not a finite number of them, but they are definitely countable. So a discrete probability distribution, when we're talking about that, we're looking at what we call the probability mass function and the probability density function. And so the probability mass function is used when we have discrete random variables, whereas the probability density function is used when we have continuous random variables. And then we'll look at a cumulative distribution function, and we've looked at cumulative functions already in an earlier chapter, and that can be used for either discrete or continuous. So the probability mass function is used when we have discrete variables. And we can look at it as the random variable x, the capital letter X, is a list of all of the values of x and their associated probabilities, which is the list of all possible probabilities of the little x. So we can say that the cumulative distribution is the probability of a random variable in terms of an observation. So two key properties when we're talking about this: the probability of each observation is a value between 0 and 1. In other words, and we talked about this in Chapter 4, probabilities always fall between 0 and 1, and the sum of the probabilities has to equal 1. So we can look at a discrete probability distribution in a graphical form, in a table, or even in an algebraic formula, and we'll look at it in all three. So let's look at this experiment. Here we are rolling a six-sided die. So the probability that we roll a 1 is 1/6. The probability that we roll a 2 is 1/6. The probability that we roll a 3 is 1/6. So for every single option, X, observation, we have a 1/6 probability. Each outcome has a probability of 1/6. If we add those all up, they equal 1. So the probability mass function is all of those together. So we would use the cumulative probability distribution when we're interested in finding the probability that a random variable assumes a range of values as opposed to just a specific value. So instead of saying what's the probability of rolling a 4, we could say what's the probability that our roll gives us a number that is less than or equal to 4. So if it's less than or equal to 4, if we're looking at the probability that it comes out to less than or equal to 4, then we would sum up all of the probabilities from 4 down. So that would be 4/6, that we would have a probability of 4/6 that we roll a less than or equal to 4. So we can look at it as an algebraic expression, and where we can say that the probability is of rolling a specific variable is 1/6. And so we can say the probability of rolling, let's say, a 5 is 1/6, but the probability of rolling a 7 is 0 because that's outside of the sample space. That's not an option. We can also graph this. So when we graph this, we're going to place the values of x on the horizontal axis and then the probabilities on the y or the vertical axis. And then we'll draw a line so that we can measure these. So here we can see the graph of where we rolled the 6-sided die. And so since the probability is always 1/6, it looks exactly the same all the way across. So this is again a discrete uniform distribution because all of the bars are the same height, so that makes it a uniform distribution. So let's look at a second example. So here we have a realtor and the number of houses that she or he is selling and what's the probability that they're going to sell 0 houses, 1, 2, or 3 houses. So we've got a couple of questions that we're going to answer. First of all, is this a valid probability distribution? Well, the first question we need to ask ourselves is, number one, do all of the probabilities fall between 0 and 1? And they do. And do the probabilities sum to 1? And if we add them all up, we get 0.3 plus 0.5 plus 0.15 plus 0.05. Those do sum to 1. So this is a valid probability distribution. If they did not sum to 1, then we would say this isn't a probability distribution. Okay. So what is the probability that a realtor will not sell any houses? Well, we're given that it's 0.3 or 30% if you prefer to convert it to a percent. What is the probability that the realtor will sell at most 1 house? So that means what is the probability that we're going to sell 0 houses or 1 house? So to answer C, we could just simply add up the probability of 0 and the probability of 1, and we would get 0.8. So there's an 80% probability that the realtor will sell 1 house at most. So now, what's the probability that the realtor will sell at least 2 houses? So that's 2 or more. Well, then that's the probability that she will sell 2 houses plus the probability that she will sell 3 houses. So that's 20% or 0.20. And then on the next slide, we will graph the probability distribution. So here's our answers. Let's check ourselves. Yes, we said this is a valid probability distribution because they all fall between 0 and 1 and they add up to 1. We said the probability of selling 0 houses is 0.3. The probability of selling at most 1 house is 0.8. And the probability of selling 2 or more houses is 0.2. So let's look at the graph now. So here we've graphed. Along the bottom, we've put our x variables, and along the y-axis, we've put our probabilities. So we can see that this graph is, number one, not symmetrical. It is skewed. It's what we call positively skewed because there's a smaller chance of selling 2 or more houses. Now let's look at, we're going to go ahead and jump into objective 2. And let's talk about the mean, the variance, and the standard deviation with respect to probabilities. So when we're talking about probabilities, we call the mean the expected value. So just know the expected value, or E, is really the mean or the average. Now to compute this average with a probability, we're looking at a long run average. So we've repeated this many independent repetitions of an experiment over a long period of time. That's how we get good probabilities. And because it is a probability, we are calculating the weighted average. So the expected value, the mean, which we denote mu, remember this, our Greek letter mu, is the sum of the probability times the the sum of the probability times the random variable, and then we'll add all those up. Now for our variance and our standard deviation, for a discrete random variable, the variance is going to be the sum of the observation minus the mean squared multiplied by the probability, and then the standard deviation is simply the square root of the variance. So here we have an example. We have Brad, who is owner of a car dealership in Chicago, and he's going to create this bonus plan for his employees. And so their bonus is $10,000. That 10, remember, is in thousands, or 6,000, or 3,000, or 0. And then he denotes the probabilities of his employees receiving each one of those bonuses. So we need to calculate the mean, or the expected value of the bonus, and then what's the variance in the standard deviation. So let's look at the mean first. So we're going to let X, the big X, denote the bonus amount. And then the value is the probability, or the little x is the observation. So the probability that an employee will get $10,000 is 15%. So to compute the mean, we need to, or the expected value, we need to multiply the 10 by the 15%, then the 6 by the 25%, the 3 by the 40%, the 0 by the 20%, and then add all that up. So the mean, or expected value, is 4.2, or $4,200. Now notice that the expected value is not one of the employee options, right? An employee can't earn 4,200. So remember, the mean is just a long run average. It's saying on average over a long period of time, this is how much, but it's not saying no employee is going to get exactly 4,200, because that's not one of the possibilities. So we can go ahead and calculate the standard deviation by taking the value of the bonus, the 10, for example, minus the mean of 4.2, and squaring it, then multiplying it by the probability. So we're going to do that for each one. So we'll take the 6 minus the 4.2, square it, multiply it by the probability, and so forth, all the way down, so that we get a standard deviation of 9.97. And then we can calculate the variance by taking the square root of that. So the square root of 9.97 is 3.158, or $3,158. So we found that the expected bonus for an employee is $4,200. And so since Brad has 25 employees, he would expect to pay roughly $105,000 in bonuses if he multiplied his 4,200 by 25 employees. So he could expect to pay out in total $105,000. Now again, no employee is going to get exactly 4,200. Some are going to get 10, some are going to get 6, some are going to get 3, some are going to get 0. But over all 25 employees, it would average out to about $4,200, give or take. Again, our standard deviation there is 3,158. So let's talk a minute about risk neutrality and risk aversion. We talked about this a little bit in chapter 3 when we talked about the Sharpe formula. But people have different opinions. Some people are risk averse and some people are risk neutral. So a risk averse person would turn down a potential gain because of a potential loss. So in their mind, the potential loss would outweigh the potential gain. Okay, or could possibly outweigh the potential gain. Thus the reason we were calculating that Sharpe formula, that Sharpe valuation, so that we could try to see if the expected gain was worth the risk. Whereas a risk neutral person doesn't care about the loss, they're only looking at the gains. So they would always accept a possibility that offers a positive gain, and they wouldn't really care about the loss. Whereas the risk averse person would say, I'm not going to accept this possibility because I might lose something. So let's look at an example here. Suppose we're told that we have a choice of receiving $1,000 in cash or we're getting a painting from our grandmother. Now, taking away the emotional side, because while I'm risk averse, my grandmother was a painter and I would take the painting over the $1,000 any day, but that's because I want to keep the painting and hang it in my house. So looking at it from a purely financial point of view, take that emotional side out of it. Okay, so maybe it's not receiving a painting from your grandmother, maybe it's just you get the choice of receiving a painting that might or might not be valuable. So here we're told that there's a possibility that the painting is worth $2,000. That's about a 20% possibility. There's a possibility that it's worth $1,000. That's about a 50% possibility. And then there's a 30% possibility that it's only worth $500. So again, taking away that emotional side, because again, if it's a painting from my grandmother, I would 100% take the painting regardless. So again, maybe we just pretend, let's just take this grandmother off. We're just going to get a painting that may or may not be valuable. Okay. What would you do? So the risk neutral person would say, hey, there's a 20% probability this is worth $2,000. I want the painting. Whereas a risk averse person would go, yeah, but there's a 30% possibility that it's worth only $500. I would rather have the cash. The cash I know is worth $1,000. That's a sure thing. Whereas the painting is iffy and I would be accepting a risk there. So first we should calculate the expected value. So we'll multiply each value, potential value, by its probability. So the mean or the expected value is 1,050, just over $1,000. And then we could again make a decision. So again, it might seem logical to take the painting because it has an expected value, a mean of over $1,000, but again, that risk averse person may not agree. And as a risk averse person, what I would be looking at is saying, look, there's a 30% probability that it's only worth $500 and only a 20% probability that it's worth $2,000. So that means the probability is higher that it's lower. I'm going to take the $1,000, right? You've heard of this saying, a bird in hand is worth more than two in the bush. That's my philosophy. But again, I am risk averse as opposed to being risk neutral.